All right, welcome everybody to today's lecture. Today we're going to take a look at stacks, and so we're going to be building upon our knowledge and things that we looked at with linked lists and move into stacks. This is just going to be an introduction, so we're going to look at some code and then kind of walk through it, how they're being how the code works, as well as a few slides here to just get the idea behind the stacks. So this isn't really intended as an in-depth study, but more of just an introduction to how they work and some code that goes along with that. The code that we're going to look at is going to be largely derived from or built off of pretty much the same code that we use for our linked list. So what you're going to see here is a lot of similarities between the two. Okay, so hopefully in looking at this, you're not, even though it's a lot of code, it's really not a lot of new. There's very few pieces in it that really change from the code that we use in the linked list. And so we'll take a look at those. I'll point those out, and hopefully you have a pretty good understanding then of what, how a basic stack works. Before we do that, we'll take a look at the next lab, Lab 9. With this one, it's I guess kind of a choose your own adventure here. And that is that I give you a couple of options. There's 3 options as far as what you want to work with. If you have an idea and you'd like to deviate from one of these 3 items, that's fine, but you do need to clear that or send me what you'd like to work on and get my approval first. If you deviate from this list and you do not get approval, then I'll just give you a 0 for that lab. So please, I encourage you, if you have ideas, to go beyond this, but let me know. Run it by me so that I can make sure it's a good lab, and we'll move on from there. If you choose one of these 3, then with these 3, use the code that we've been working on. Feel free to use the linked list code, use the stack code. You don't have to write. I'm not expecting anybody to write anything from scratch here. If you want to, you certainly can, but I'm definitely not expecting that. So you can use the code that we've been using in class, code that we'll look at today. It's all uploaded into D2L. Plus a lot of this, especially for linked list, stacks, and queues, the topics that we'll use, that we'll look at here to wrap up the semester, all of that's coming straight out of the book. So you can download it off of the book's website as well. But I provided it all in D2L. So please feel free to use that to build off of, to build up for your lab. So if you have any questions, any doubt, if anything is not clear exactly what I'm asking or where you should head with that program, don't hesitate to reach out. Don't hesitate to send me an email. Send me as many emails as you need until you understand or feel comfortable as you start working on your program. If you want feedback, again, feel free to send me as many emails as you want. I can look at your code as many times as you want to help make sure that you're on the right track and you're understanding these concepts that we're talking about. Okay, so that's uploaded to D2L. Go ahead and check D2L, take a look at that, check D2L for due dates, and again, let me know if you have questions. All right, so with that, we'll go ahead and we'll get into our stacks. You can see we have a relatively short presentation here because, again, the concept and the code that we're going to look at is very similar to what we use with linked lists. We're going to constrain them, so there's just some very simple modifications that we're going to make. So what is it? Well, it's essentially a constrained version of a linked list. And how is it constrained? Well, with a linked list, as we add new nodes, let's say that we're looking at our insert function without maintaining a sort order. As we'd insert a new node or we'd add a new node, add it to that linked list, we'd always add it to the end. And so our pointer would keep track of the front, and then we'd have to find the end of the linked list by looking for that next node pointer that was null. With a stack then, we're only concerned about the top of the stack. Okay, so new nodes are added to the top of the stack and new nodes are removed from the top of the stack. And so this pointer, we're going to have a pointer that keeps track of the front of the linked list or the top of the stack, and that's the only pointer value that we're going to manipulate. As we add a new node, it's going to point to the new node. As we remove a node, it's going to point to the value that was below it. Okay, there are two, the concept associated with that is typically LIFO, so last in, first out. The last one in is going to be the first one out because the last one in is going to be the value, or in the case of the code we're looking at, the node that's at the top of the stack, so that when we remove an item, the last thing that was in is going to be the first thing that's out. Here you can see a little picture, a diagram. Okay, we have 2 main operations that we deal with when we're talking about stacks, pushing and popping. Pushing adds a new item. Okay, so we have this one-way direction. Let's see here, get a pen and I want to change, no, that should be good. Okay, so we have our push, and pushing is adding to the top here. Popping removes from the top, right? And if we think about our linked list, okay, we typically think about stacks in the vertical here. And when we talk about linked lists, we typically look at linked lists kind of in the horizontal. And so let's say that this is our linked list, and we have these boxes that represent these nodes. Okay, same thing here. If we're thinking about this more in the horizontal, you know, we're trying to correlate this real loosely to how our linked lists work. You know, this is the end of the linked list. This is the front or the top, and so we would add new items to the front. Okay, we just take this and rotate it. So we kick this side out and rotate it. And I know this is probably terrible, but I'm just trying to help, I guess, with the learning curve here by associating a little bit more with linked list. Okay, so again, top of the stack, this was the very first item pushed in, and when we pop, it's the last item. Okay, so it would be whatever comes in the top. We're still gonna use nodes. Okay, so just like with our linked list talk, these boxes here, we can use those to represent our nodes. And the nodes are going to be a struct, and they're going to have two members. They're going to have the data member that holds the value. In the case of the code that we're going to look at today, let's say that it just holds simple numeric values or integer values. And then it's going to have a second member, which is a pointer. And that pointer is going to be the next node or the next item pointer. Okay, and it's just simply going to be what builds our ability here to create our stack. Okay, so it's identical into the way that we built the linked list. Okay, so what are some of the differences? Well, with linked lists, we can insert, we can delete anywhere in the linked list. Okay, that was one of the benefits of the linked list. You know, it operates conceptually much like an array, but with a linked list, let's say when we looked at that insert with sort order, we could identify anywhere in the linked list we wanted to insert a new node, and we simply have to change where those member pointers are pointing to. We just have to simply add that new node into that linked list. Same with deletion. With deletion, if we want to remove any single node from the linked list, we simply identify what node we want and we delete it. We remove it, we link the nodes in between to each other, and then we free the memory that node was allocated. With stacks then, stacks only occur at the top. Okay, so if we want, let's say that we have a stack and it has several items on it, and we want the value from the item at the bottom of the stack, the only way that we technically can get to that item is if we pop all the values off the stack. Okay, that's the only way we can get there. Now, we could technically in our code, you know, we can iterate, we can traverse the nodes and see the values. We could technically traverse to the bottom of the stack and find them, but that's not how they typically work. We typically only have push and pop, and if we want to get a value that's on the stack, that's within the stack somewhere, and it's not on the top, we have to pop until we reach that value. Okay, so there's our two functions, push and pop. I think we talked about those enough at this point. We're going to take a look at stacksintro.c. I've uploaded that to D2L, and we're not going to necessarily create them. These have already been created, but what we're going to look at is functions that print the stack. We're going to focus our conversation on the push and the pop, and then check if it's empty. And again, I think you'll see that all of these functions are going to look relatively, printing the stack, checking if it's empty is almost going to be identical to the linked list, and then pushing and popping is going to look very similar. The only real difference here is the constraints. The fact that when we push, we're adding a new node to the top of the stack. When we pop, we're taking a node off the top of the stack. That's the only thing. So you're going to see some of those constraints built into these functions. Okay, so here's our code. Make this a little bit bigger. Okay, here's our struct, self-referential structure. Okay, so nothing new here, right? We have one member for the data, and then we have another one that is a pointer to the next node. Okay, so we're going to use these exactly the same way that we use them in the linked list. Next, we have a couple type definitions. Again, these are the same format or the same way that we use those type definitions for linked lists are going to be used here as well. And that is that we have one type definition for the struct stack node, and then we have another type definition for a stack node pointer. Okay, so they're using the same thing. They're named different, obviously, because we're changing concepts. We're talking about stacks, but they're being used in the exact same way that we use them with linked lists. Here's our prototypes. So we have push, pop, is empty, print, and instructions. Okay. From there, we can take a look at the main program. And here we start off with declaring our stack pointer. Set it equal to null at this point because the stack doesn't exist. Okay, this value is what we're going to use to keep track of the top of the stack. Okay, and so we have these comments here that were left. These are actually comments by the author of the book, and they're just left here as reminders in order to give us some insight into what these things are doing. I'd say we could probably come up with a better variable name to eliminate this comment and make it redundant, but we'll save that for another day and another topic maybe. So we declare that pointer. Okay, the whole purpose of this pointer is simply to keep track of the top of the stack. That's all it's going to do. So just like we had one with our linked list, it kept track of the front of the linked list. This one's going to keep track of the top of the stack. We have choice and value, and these are going to simply be variables that we use in order to drive this menu. So at this point in time, you've seen this menu, you've worked with this menu, at least you did on lab 7, and so you should have a pretty good idea what this menu is doing and basically how it's working. We call our instructions function. And if we scroll down a little bit here, you can see what does instructions do. Very simply, it's just one big printf. It just prints off essentially the menu options here. So 1 to push, 2 to pop, 3 to end the program. And we'll see that logic implemented when we look at the actual structure, the rest of the structure of this main function here. We print a question mark, and then there's a scanf %d with the choice. Okay, so question mark is just simply being used to try to indicate that the system is ready to accept input. It really doesn't mean anything other than that. It's completely arbitrary at this point. And then our scanf. Okay, so then we're storing the value that the user enters into the choice variable, and then we're using that choice variable inside of a while loop. So we're saying that while choice is not equal to 3, then enter into this while loop. Okay, so what is case 1 and case 2? Case 1 is push, case 2 is pop, default is invalid, and case 3, we know if we go back and look at our instruction, simply is to end the program, right? So in this case, if they enter 3, it breaks the loop. We can trace that end curly bracket here, end of the while loop, so it's been commented for you to help keep the curly brackets matched up for you. End of run, and then it returns 0. Okay, so program termination there. Okay, what happens in the while loop then? Okay, so choice. Choice is what the user enters. Okay, and this isn't robust. This isn't really validating. You can enter in a char character, and you'll see things will blow up, and the application won't work fine. We're going to assume that the user is going to enter 1, 2, or 3 at this point. So if they enter 1, we'll do a switch on 1. Case 1 is push value onto the stack. Okay, so if we want to push a value onto the stack, we need to get a value from the user. So we print off, we ask them to enter an integer value, they enter that integer value, we store that value that they entered in the value variable. Again, we're just going to assume that they're going to enter something that's an integer, and then we call our push function. Okay, so let's scroll down here. We'll take a look at push. All right, so push is fairly simple. And let's see, I'm going to go back into these slides. Maybe I do a little bit of drawing, so hopefully my drawing skills can carry us through. The drawing skills on a PowerPoint presentation can carry us through this explanation here. So I'm going to change colors. Let's pick out yellow maybe. Okay, so here is our function. We're going to look at the push function. And let's say that we already have just an arbitrary amount of information already in a stack. So let's say we have these 3 nodes, and they just contain, really doesn't matter, but let's just say they contain some values, right? Because that's what our struct holds, is numeric values. So the first thing we do, the first thing we need to look at is we have the 2. Okay, so we have the pointer to a pointer, which is the top pointer. Okay, so the value that we're providing for this first argument is the value of, it's the actual memory address of our stack pointer. So that stack pointer that was declared at the beginning, in the beginning of the application. So we're going to use that to keep track of the top of the stack, right? Because if we're pushing onto the stack, then we're going to change where that needs to point to. The second argument then is simply what we're pushing onto the stack. So in this case, they called it info. I think that's a bad variable name. It's the data. It's whatever we want to actually push, right? So in this case, again, it's a numeric value. Okay, so we have our new pointer. We need a malloc memory for that new pointer. This is going to be our new node. So let's say that we're essentially, if we're still kind of looking at this like nodes from our linked list. We're going to create this new, we're going to malloc memory for this new node, and it's going to have whatever value is passed to it. Okay, that's where new pointer is pointing. So I'm just going to say, let's just do that to make it a little bit easier. Okay, so that is pointing to new pointer. This has some arbitrary memory address, right? Right, our stack pointer, and I'm going to make that just a shortcut and say that it's SP, right, for stack pointer. Right now, that's pointing right here, and all of these have, you know, some sort of memory address. Right? So we'll just go ahead and try to shortcut that because it's hard to write. After we have malloc memory for that, then we check: did we get memory malloc? What will malloc return if it wasn't able to get the memory you requested? It'll return null. So if new pointer is equal to null, we didn't get the memory we requested, so we go down the else branch and we don't do anything. If it's not equal to null, then great, we got the memory. So now this is pointing to that memory address that we've been assigned. So from there, we say new pointer's data member equals info. Okay, so I guess I got a little ahead of myself, but we update that data member to there, and we say that new pointer's next node equals the top pointer. Okay, top pointer was our stack pointer. So now its next node member points to here, because that's where the stack pointer is currently, that's where that pointer is currently pointing. Okay, then we say top pointer equals new pointer. Right, so now instead of this, let's change the color to red. So instead of this pointing, our stack pointer pointing there, it now points right here. Right? And this essentially becomes the top of the stack. So now our stack pointer is pointing here. Our new pointer is pointing to what was previously on the top of the stack. This one points to what was on the top of the stack before it was pushed, and so forth until we get to the bottom of the stack. And that's it. Okay, then we're done. So that function ends. Get out of there. And if we go back to our case statement, okay, so we're back in our function main. We're inside of the loop. We're inside of our switch. We just went into this first case because let's say I selected menu option 1. We just finished executing our push. Okay, so the user entered a value, and now we push that value onto the stack. And now we simply print the stack. So if we scroll down here, print stack is right here. And you should see this is identical to our linked list when we print the linked list. We pass, what do we pass? The value of our stack pointer. Okay, that matches up. That's what our argument is. It expects a memory address. So if it's equal to null, then we have an empty stack, right? But in this case, we just got done pushing, so we know for sure we don't have an empty stack. So we say the stack is, and while current pointer is not equal to null. Okay, in this case, okay, again, same concept. We're still, it's like if we're looking at this as a linked list, we're looking for that next node member that's equal to null. And so that in this case, in the context of a stack, the next node member means we've reached the bottom of the stack. So we say, all right, current pointer is not equal to null. That means I have a node, I have an element, I have something that's been pushed on that stack. I'm going to go ahead and print that data member because that's the value that I'm looking for. And then I'm going to increment the current pointer equal to its next node member. Right? And then we'll iterate around again. Well, current pointers, if it's not equal to null, we'll print that data member, we'll move to the next node. And then we just walk down that stack until we get to a null value. Once we get to the null value, that means we've reached the end. Okay, so we can go ahead and see how this program executes. Make the code a little bit bigger. Intro.c. Okay, there we go. All right, so we're in our menu. Let's say that I enter option 1, I enter an integer value, and I'll say 3. Okay, the stack is 3. Okay, one item. So the top of the stack is item 3. Let's push on another item. Let's say 2. Okay, null represents the bottom of the stack. I had a 3 previously. Now I pushed on a value of 2. So 2 is now the top of the stack. So looking at this horizontally, the left is the top, the right is the bottom. Okay, let's push another value on. Let's say that I push on a value of 1. Okay, 1, 2, 3. Let's say I push on a value of 99. 99, 1, 2, 3. Right? We just keep pushing on to the top of the stack. Now let's say that I want to pop a value off. Okay, so I hit 2, and what happened? Okay, that occurred right here. I didn't have a choice. Okay, when we pop, we're just taking off the top of the stack. Okay, before that, this was the state of the stack, 99, 1, 2, 3, null. And so when I popped, you can see we got the value of 99 was popped off, and now this is our new stack, 1, 2, 3, null. Okay, and then we can just keep doing that. Oh, I hit end, wrong one. We just keep doing that until we get to the end of the stack, until the stack is empty. And then the program would simply tell us your stack is empty. Okay, so what does pop look like? Okay, well first I guess let's take a look at it in the case. And so let's say that I chose menu option 2, hit enter. That would match case 2. As long as the stack is not empty, we don't want to try to pop something off an empty stack because depending on how we implemented it, that could result in a segmentation fault. If it's not empty, then we go ahead and we call pop. And in order to do that, we have to pass the memory address of our stack pointer, right? We have to say this is the top of our stack. Go ahead and remove that value. So go ahead and we'll take a look at pop. Let's try a yellow again. Okay, we'll create some arbitrary nodes here. Let's say it's 1, 2, and 4. Okay, so we're a stack pointer. And now it is pointing right here. What is this code doing? Okay, so we create a temp pointer. Change colors. So I'll call this TP as in temp pointer. Right, so stack node pointer, temp pointer. Okay, right here. We haven't assigned it anything. We haven't assigned a value to it. We should probably make it null though. We have pop value. Okay, so we declare an integer variable. We're going to use that variable to store the value that we pop off the stack. We now say that temp pointer equals the top pointer. Okay, so temp pointer is now pointing where our stack pointer is pointing to. Okay, so right now they're both pointing to the same location. Pop value equals top pointer's data member. Okay, so now if we look at, I'll just call that PV, and it's equal to this data member. Okay, so we assigned it a value equal to 1. Okay, now top pointer equals top pointer's next node member. So we got to change. We're removing a value from the top of the stack. Let's see here. So instead of pointing here, we're pointing at this next node member. What does that do? That means that our stack pointer is now pointing right here, right? Because we're about to get rid of this value. Okay, so pop value or top pointer equals top pointer's next node member. Okay, once we've done that, our stack pointer is pointing here. Now we can free the temp pointer. Okay, that's why we had temp pointer, because we're going to change where stack pointer is pointing to. We got to keep track of this memory address for this top node right here because we want to free it. Okay, and that's what we just did. So we said free to whatever temp pointer is pointing to, in which case that gets rid of that node, and then we'll return pop value. Okay, so in this case we return 1. Right? When we free the memory of something that's malloc, we can only call free on memory that's been malloc. Once we've done that, it's gone. It no longer exists. That memory has been reallocated back to the system, and we're not going to be able to reclaim it or reuse it. Okay, so that's why we store that value in that pop value variable. And that's it. If we go back to our code, that's why when you can see here that we have a function call inside of this printf. Okay, this function returns a value, or returns the integer value that we just popped off the stack. And so we can use that return value from that function call for the format specifier as one of the arguments in that printf statement. Okay, so that's it. That's print stack, push, and pop. Is empty. Okay, I guess we could look at that real quick. It's pretty straightforward. If the pointer is pointing to null, then we're going to assume that it's empty, because if the pointer is pointing to nothing, we have nothing. We have no nodes to reference. Okay, so it's empty. All right, and that's it. That's our code. Okay, so take a look at this. Run the program, trace the code, make sure that everything that's happening in here makes sense. You can use this code as the basis for, if you choose anyway, for one of the for one of the topics in the lab, for Lab 9. If you don't understand anything, let me know, because this is probably as deep as we're going to go with stacks. And then next week we'll look at queues, and we'll eventually move into trees as well. So we'll look at a couple more data structures before we wrap up the semester. So any questions, let me know. Otherwise, we'll talk next week. Thanks. Bye.